right, so we are looking at probability of compound events today. The first slide just kind of reviews what probability is, and then we're going to jump into the stuff that's a lot tougher. So our objective is to find theoretical, experimental, and geometric probabilities. We're not doing all of that today, but we'll get into some of these. The theoretical probability that event A will happen. Here's the P stands for probability, and then the A in parentheses means that A will happen. So this says the probability that A will happen is the number of outcomes in A over the total number of outcomes. This always makes more sense with an example. So here's a spinner. It's numbered 1 through 8. So the probability of getting a 3 is 1 out of 8. You guys are so smart. So this is going back to some of the stuff you did a long time ago. Probability that you will get a factor of 8. So let's see, that would be 1, 2, 4, and 8. So that's 4 out of 8, which reduces to 1/2. You could also write that as 0.5 or 50%. So I'll write down those factors just so we have it in the notes. Okay, so the probability of getting a prime number. By the way, number 1 is not prime.
Right.
2 is prime. 3 is prime. What else?
6 and
So we have 2, 3, 5, 7. So that's also 4 out of 8, which is reduces to 1/2. What's the probability of getting a 9 on this spinner?
0.
0, because there are no 9s. Okay, so if you get a probability of 0, so below this box, we'll just draw this little continuum. So if we're looking at probability of 0, that means it's not gonna happen. Not gonna happen. Gotta write it that way. Not gonna. Okay? Over here, if you have a probability of 1, which would be the same thing as 100%, it means it's gonna happen. And then everything in between would be along this continuum. If it's 0, it's not gonna happen. If it's 1, it's definitely gonna happen. And then all of these other probabilities fall in between. A half would be halfway. You guys know the drill. So this just is kind of reviewing what we've had before. All right, so now we're going to jump into the more high school part of this, where it's going to use some of our combinations stuff. So it says 4 cards are drawn from a standard 52-card deck. What is the probability that the first 3 cards are black? Okay? So the first thing that we need to know is how many black
13.
cards are in a deck. There's more than 13.
What if you don't know that's general information?
Yeah.
So you're going to have to figure it out. So you could count all your cards.
26, right?
So there's 26 because you could have spades or you could have diamonds, and there's 13 of each.
Oh, you can have spades.
Okay? So if we're trying to figure out, so the black cards, the spades, and the clubs, thank you. We could do a combination of 26. There's 26 of them in there. And we're looking for how many of those, how many different ways we could draw 3 of them that would be black. So this is like how many ways that we could get I should write combinations of 3 black cards. So it's the different ways you could get 3 black cards out of the 26 cards that you have. And then on the bottom of our fraction, we're going to look at all the combinations of 3 cards in general. So it tells us there's 52 cards. And so you're drawing 3 cards at random. And so this is the different combinations of just 3 cards out of everything. So this is all the different ways you could get 3 black cards. This is all the different ways you could get 3 any kind of cards. And so if you do those, you get 2,600 over 22,100, which is a large fraction. And there is a way to reduce that on your calculator. It comes out to be 2/17. So who has a calculator I can borrow since mine is... What?
Why is it better to do it like this than 26 over 52 times 25 over 51 times?
I'm not sure. Does that give you the 3 different ways you can get black cards out of the 3 ways you can draw 3 cards out of 52? I'm not sure that you would get the same number.
It gives you the decimal, but then you can go to fraction.
Okay, so... Alright, I don't know. Alright, so 2,600 divided by 22,000 100. We get, so you give you a decimal, you can change it to a fraction by using the math key. So math, and then you want number 1 fraction, and it'll change it down to 2/17. So what were you saying, Johnny? I just have to think through what you were saying.
So
So
there's
it's the
a
probability-
26 out of 52 that the first one's black. And
Okay.
then if the first one's black, there's a 25 out of 51.
So
If the
26
second
out of 52, 25 out of 51. Does it give you the same answer?
one- I don't know.
24 out of 50. So we'll try that really quick.
Go
It
away,
probably
it's awful,
does.
sorry.
So 26 times 25 times 24 on the top. And then I'm doing this on a calculator. 52 times 51 times 50 on the bottom. I'm going to take this number divided by that number. It does work.
Ayo.
So I think the idea here was just we were showing you how you could use the combinations. And this way you wouldn't necessarily have to, well, I guess you still kind of have to think about it. All right, so let's look at the next problem. So it says 5 cards are drawn from a standard 52 card deck. What is the probability that the first 5 cards are spades? So you want to try this Johnny's way? So there would be 13 spades out of 52, and then once you draw a card, you're not putting it back. 12 out of 51, 11 out of 50, 10 out of 49, and 9
Whoa.
out of 48. So that's
We should do
one
ours,
way.
too.
That's one way to do it, and I don't know what that's.
If it's shorter, it's probably faster.
And so the way that it was in this PowerPoint that I have, they had you taking, okay, so there's 13 spades and you're getting 5. And then there's 52 cards that you're drawing 5. And they just used that little probability button. And we should get the same answer either way. So I guess you guys would have a choice. And it comes out very, very small. It comes out 0.000495 something, something, something. And based on what I'm seeing in my notes, I think we couldn't get it to convert well to a fraction, so we just left it in decimal form. Yes. Yes. Okay, so basically this is almost 0. We could interpret this that there is a very small chance that you're going to get 5 spades the first time you're dealt 5 cards. I'm trying to think in poker, what is it when you have all 5 from the same suit and they go in
Or
order?
royal flush.
No, that's not.
Yeah.
Is it?
Whenever they are in order in the same
You know
suit,
everything.
it's a royal flush.
Okay. I thought for a royal flush you had to have like the kings and queens. So I was just thinking like 5
Oh,
spades.
for the top ones. And then it's a flush if it's
So it's
just in
straight
order,
if you
it's
have,
just
like-
in the same suit.
If it's in the same suit, it's a straight. So this would be your chances of getting. Well, this wouldn't even be of getting a straight. It'd just be getting 5 cards that are all spades. So this,
Yeah,
so
that
your
could be a
chances of getting a
flush.
straight would be even less to get it on your first time of drawing. All right, let's not talk about gambling. All right, so let's look at the next part of this. So this was just kind of how we can use some things we already know. Now we're going to get into the real heart of what I want to cover today. So it says our objective is to find probabilities of union and intersections of 2 events. We're only going to do unions today. And use the complement to find the probability of an event. So if A and B are 2 events, then the probability of A or B happening works like this. You're going to find the probability of A happening plus the probability of B minus the probability of A and B, which is a little interesting, but you're basically taking out the things so you don't count them twice. And then if A and B are mutually exclusive, meaning that there's no overlap, then you can just do the probability of A plus the probability of B. So we'll just have to think through some of these. There's a cool picture that sort of explains what they're talking about with union and intersection.
You said that this hour I could do
The end of this hour or beginning of 7th hour. Right now I'm teaching.
Okay.
Okay? 7th hour is better. All right, so if you have the union of A or A and B, that is what we call our OR problem. So I'm just going to kind of put that at the top. These are the problems where they're going to give you OR. And so, oh, you can't see what I'm writing. So union of A and B is an OR problem. Okay, so I'm going to highlight this. This is a little Venn diagram. And this is the probability of A happening. Okay? But evidently there's a little bit of overlap with event B happening. So if you want to color this, you can. So I'm using 2 colors so you can kind of see. When you're doing an OR problem, this is why if they're not mutually exclusive, this is all the ways A can happen, this is the ways B can happen. You would be counting some events twice. And so that's why you would have this overlap right here. And so for OR, you want to have all of it in there, but you don't want to count anything twice. So if you have an OR problem, you're looking for everything in A and B and where they overlap, and then you subtract anything that's counted twice. Okay? When we talk about an intersection, I'm going to use the same. We're just talking about the place where the 2 events meet. So an intersection is a problem where they're going to use the words and or something like both. What's the probability of both of these happening, or of A happening and B happening? And we've encountered some of these that we just kind of did with the fundamental counting principle. Okay, so then there's like one more slide. I thought these were interesting. They're not. All right, so and they're not interesting. I didn't finish my sentence. They're not examples of what you're going to see on was what I was trying to say. Yeah, that came out kind of funny. Okay, so the intersection of A and B. So these are what we would call mutually exclusive events. So as you can see, there is no overlap. A is one thing, B is another thing. They're never going to happen at the same time. And so if you are looking for the intersection of these, of things that happen, there you go, I'm sorry, of things that happen in A and B, so this would be an and problem. Looking for things that happen in A and B and they're not intersecting at all, then you're going to have you're going to have no solutions, which is called the empty set or null set. It has different names, and that's that.
There's a set containing all sets.
So it's a set with nothing in it. So there's no overlap here. So they're mutually exclusive, which means that there's just no overlap between A and B. They don't cross. Nothing is happening in both places. Okay, so we're going to take a look at some mutually exclusive events and then some compound events and kind of talk our way through each of these. I'm not doing a great job of explaining today, but I'm going to try to pick it up. All right, so probability of mutually exclusive events. It says a die is rolled. That's like one dice. One is called a die. What's the probability of rolling a 2 or a 6? So we're looking for the probability of 2 or 6. So because we're rolling 2 different times, that's 2 separate events. So the probability of rolling a 2 and the probability of rolling a 6, we're going to do both. So the probability of rolling a 2, there's 1 2 in a die, so that's 1 out of 6. And the probability of rolling a 6 is 1 out of 6. And so we get 2 out of 6, which is 1/3. Okay?
I'm so smart.
Because so basically the reason they're mutually exclusive is what you rolled the first time does not affect what you roll the second time. They're separate rolls. Okay? Then it says a card is randomly selected from a standard deck of 52 cards. What's the probability that is a 2 or a king? So we're looking for the probability of a 2 or a king. I'm going to use K for king. So the probability of it being a 2, how many 2s are there? So there's 4 2s out of 52 cards. And then a king would be 4 out of 52. So you get 8 out of 52, which reduces to 2/13. Okay? So these are 2 different things. It can't be a 2 and a king at the same time. So that's why they're considered mutually exclusive. It's either going to be a 2 or a king. It can't be both. Okay? So now we're going to look at some of the events that are not mutually exclusive. So down here we've got the probability of a compound event. It says a die is rolled 1 time. What is the probability of rolling an odd number or a prime number? So we're looking for the probability that it's odd or prime. Okay? So let's talk about odd numbers. So on the die, there's 1, 3, and 5. So technically that's 3 possibilities out of 6. Prime numbers, we do not count 1. So that is 2, 3, or 5 are the prime numbers. So you can add another 3 out of 6. But then we have to subtract the numbers that are getting counted twice. So 3 and 5 are on both of those. So we're going to subtract 2/6. We end up with, so 3 plus 3 is 6 minus 2. And so we get 4 out of 6, which is 2/3. I'm going to go to the margin, but it's okay. Does that make sense?
Yeah.
So you're adding this one plus this one and subtracting out the ones that happen on both sets. There are other ways to do this. A lot of the things we're going to do, we're going to see how to do it several ways, and you guys will be able to pick when you get to the test how you want to do it. Okay, so on the next part, it says a card is randomly selected from a standard deck of 52 cards. What is the probability that it is a red card or a king card? So we're looking for the probability that it's red or a king. Okay? So the red cards, it's 26 out of 52 because it would be half of them. And then how many kings are there? 4. So 4 out of 52. Then we have to subtract.
Minus 2 because there's 2 red.
There's 2 red kings. So we're going to subtract out the 2 red kings. So we have 26 plus 4 is 30 minus 2 is 28. So we get 28 out of 52, which reduces to 7/13. And something I hadn't really talked about, but I think you guys probably did in middle school, you can divide these and write them as a decimal. You can also write them as a percent. Fractions are not the only way to write the answer. It is what we're going to use mostly because it works so well with the formula. But if you wanted to divide 7 by 13, you'd get about, it's roughly 0.54, which would make it roughly 54% chance. In real life, a lot of times they're going to say, oh, the probability is 54%, and they're going to use that 54%. And so I just want to remind you guys that you can do that. I think you know that, but just feel obligated to bring that up. All right, so let's look at the next one. This one's a little longer. 25 students are on the Jefferson Middle School football team. 6 of them take algebra, 12 of them take biology, 15 students took algebra or biology. What is the probability that a student took both algebra and biology? Oh my goodness. So what we're going to do is we're going to find the probability that they're taking algebra. We're going to add it to the probability that they're taking biology. And then subtract the probability that they're doing both. That's what I have written down. And then, and we know that there's 15 that took one or the other. And so that equals 15 out of 25. So it's sort of like an equation. Sorry, I wasn't explaining that well. So we're going to find out how many are in algebra and how many are in biology, but we know some of those overlap. And so we're looking for the probability that they're both, and we know that there's 15 out of 25 that are either here or here. Super complicated. All right, so the algebra, so there's 25 students, and we know 6 of them take algebra, so that's 6 out of 25. There's 12 taking biology, so 12 out of 25. We don't know how many there are for both. So the probability of both, if you want, you could just put an X there if that's something you're more comfortable with thinking about equations. Over here we have 15 out of 25. So if I add these together, I have 18 25ths minus X equals 15 25ths. So we could go all algebra-y, or we could go, okay, what would I subtract from 18 to get 15? 3. So then the probability of getting both would be 3 25ths. Does that make sense? Because you're going to keep the same denominators of 25 all the way across. So I was just using a little logic there. Instead of subtracting 18 25ths from both sides, dividing by -1. We can just see it's 18 minus X is 15. So it's 3 out of 25. Or you could write that as 0.06, or you can write that as 6% if you want to compute that. All right, so we're going to look at the probability of the complement of an event. So this has got some weird notation in it, but it's not difficult. The event A prime, so this little mark after the A, we read A prime, is called the complement of event A, and it consists of all the outcomes that are not in A. So basically, the probability of the complement of A is written this way. The probability of A prime. So this is like basically the probability that it's not A. And so basically what you do with that is you can take 1 and subtract the probability that it is A. And so 1, remember that 1 is the same thing as 100%. So they call it the complement. It's basically, this just says the probability that it's not A. They came up with like a special notation. A lot of times I just write the word not because I forget what the prime means. I know it's bad as a teacher, but it's true. All right, so a card is randomly selected from a standard deck of 52 cards. What is the probability that it is not a spade? So the point of this slide is to show you, so we're doing P, that basically it's not a spade, which you could do directly, but I'm supposed to show you how you can do the complement. So we could take 1 minus the probability that it is a spade. And so you'd have 1 minus 13 out of 52. And so basically, we could change 1 to 52 over 52 minus 13 out of 52, which gives you 39 out of 52, which reduces down to 3/4. For this particular example, I probably would have just figured out how many cards were not spades to start with. But sometimes if you are given a percentage or a decimal, that's where this comes in a little bit more handy. And so there's an example of that on the next slide where they don't even give us a story problem. So they say events A and B are mutually exclusive. Find the probability of A or B. So they're just saying the probability of event A happening is 0.4. Probability of B happening is 0.5. And so the probability of finding A or B, you just use the formula. So we want the probability of A plus the probability of B minus the probability of A and B. Oh, they're mutually exclusive, so we don't have to do that part. So basically all I have to do is add 0.4 and 0.5 together to get 0.9, which you could also write as 9/10 or 90%. So a lot of this is just giving you another way to look at it, having you do more than one event at a time. It's not super complicated.